This is the EdExcel AS Level Further Maths Paper 2, covering the Decision 1 D1 module, and this paper is from the 2022 series. Question number 1. The list of 11 numbers shown above is to be sorted into ascending order. For part A, we have to carry out a quick sort to produce the sorted list. You should show the result of each pass and identify your pivots clearly. For part A, you can see here we've got a list of 11 numbers. Now the middle entry will be the 37. So everything smaller than the 37 we write to the left, everything bigger than 37 we write to the right. So 34 is smaller than 37. Then 28 is smaller than 37. 33 is smaller than 37. And then we've selected 37 to be our pivot. And then what's bigger than 37? We've got the 55. We've got the 44. We've got the 59. We've got the 41. We've got 52, 42, and 47. Now you can see we've got two sublists. So now we need to sort these. Now before anything else, the 37 remains where it is. And from this sublist, we can identify the pivot to be 28. And from this sublist, we can identify the pivot to be 41. Now, from this sublist, the 34 is bigger than the 28, and the 33 is bigger than the 28. So the 28 would go here, and then we've got 34 and 33. Now you can see that 55, the 44, the 59, the 52, the 42 and the 47 are all bigger than the 41. So 41, our pivot, goes here, and then what's bigger than the 41? We've got 55, 44, 59, 52, 42, and 47. We've got a sublist here and a sublist here. Now before anything else, the 28 remains where it is, the 37 remains where it is, and the 41 remains where it is. Let's now identify our pivots. If we choose the middle right, we've got 33 as a pivot, and we would have 52 as a pivot. Now the 34 is bigger than the 33, so the 33 will go here, and then here we would have the 34. Now you can see the 44 is smaller than 52, and the 42 is smaller than the 52, but 55 is bigger than 52, Same with the 59, and the 47 is smaller than the 52. So we've got 52 as our pivot, and then 55 is greater, and 59 is greater. We've got 1, 2, 3 sublists. Now, the 28 remain where it is. Same with the 33. Same with the 37, the 41, and the 52. Now, the 34 is in between the 33 and the 37, which are both pivots. So the 34, we've got nothing to compare it with. And now for this sublist, the middle entry is the 42 and the middle right is 59. Now 44 and 47 are both bigger than 42, so 42 would go here, and then we would have the 44 and the 47, and then 55 is smaller than 59, so 55 goes here, and 59 is our pivot. Now the 28, 33, 37, 41, 42, 52 and the 59 are unchanged. Similar to before, we've got nothing to compare the 34 with, so the 34 remains where it is. And the 55 here, we've got nothing to compare it with. The 55 is in between the 52 and the 59, which are both pivots. And if we select the middle right, that will be 47. Now 44 is smaller than 47, so 44 goes here, and then the 47 would go here. Now you can see the 34, the 44 and the 59, we've got nothing to compare those with because they are in between pivots, and therefore the sort is complete. For part B, we have to use Kruskal's algorithm to find the minimum spanning tree for the network in figure 1. You should list the arcs in the order in which you consider them. For each arc, we have to state whether or not you are adding it to your minimum spanning tree. Now here is a copy of figure 1, and what you will notice is each of the weights on the arc correspond to the list of numbers we see here, and for this list of numbers we have already put them in order. So the smallest is the 28, which would correspond to DE. So we have DE with a weight of 28. Next, we have 33, which corresponds to CF. So we have CF with weight 33. Then we have the 34, which would correspond to the CD. So we have CD with weight 34, and then we cannot include the 37, which would correspond to CE, otherwise we would have a cycle. So this CE with weight 37 would have to be rejected. After that, the 41 corresponds to the BC. So we have BC with weight 41. And then we have EG with weight 42, and we can use EG. We don't get a cycle, so we have EG with weight 42. Then we have 44, and that corresponds to FG. But the problem with FG is, if we use it, we would have a cycle, and therefore the FG with weight 44, we would have to reject. And then we have 47, which corresponds to BD, but the problem with using this, we would have a cycle, so the BD with weight 47, we would have to reject. And then we have 52, which corresponds to AB. So we have AB with weight 52, and then we have the 59, which would correspond to rather here we have 55. So next we have the AC, which we can't use because we'll get a cycle. So AC with weight 55, we would have to reject. And then we've got DG as well, which we would have to reject with weight 59, because otherwise we would get a cycle. So here we have the weights which we can use, and those which we rejected were clearly stated. Now we have to draw the minimum spanning tree on diagram 1 and then state the total weight of the tree. Well, here is the minimum spanning tree, and to find out what the weight is, we've got 52 plus 41 plus 34 plus 28 plus 33 plus 42, that's 230. So the weight is equal to 230. Question number 2. For part A, we have to draw the activity network described in the precedence table above using activity on arc. Your activity network must contain the minimum number of dummies only. So what we can see is A, B, C and D depend on nothing. So if I just draw this at the side over here, I've got A, B, C and D depending on nothing. So here is my source. E depends on A, so E goes here. F depends on A, B and C. So suppose F goes out over here. Well, F depends on B and C as well, which means I need a dummy over here and I need a dummy over here. Then I've got G, which depends on C, so that's fine. Then I've got H, which depends on C. Then I've got I, which depends on E, so I goes here. And then I've got J depending on E, F and G. So if I have J going out over here, well, it depends on E as well, so that means I need a dummy here. And it also depends on G, so we can extend this line to this point here. And then K depends on D and H completing. So I've got K over here. Now let's finish off all these so that they join a common point like so. So here is the activity network, and now let's draw this neatly. So here is the completed activity network. For part B of the question, we have to explain why it's necessary to draw a dummy from the end of activity A. So we've got this dummy activity over here at the end of A. Now the reason we must have a dummy is because activity E, this depends on just A, but activity F depends on A, B and C, which is why we need a dummy at the end of A, as we see here. Next, every activity shown in the precedence table has the same duration. We have to state which activity cannot be critical, justifying your answer. Well, if we think about it, activity D cannot be critical. Bearing in mind, each activity has the same duration. And the reason activity D cannot be critical is because activities C and H can't be finished before D. So for us to start K, C needs to finish, H needs to finish, and D needs to finish. Which means activity D has some flaw in it because D is waiting for C and H to finish, and therefore D cannot be critical. Question number 3. For part A, we have to explain what is meant by the term path. Well, a path is a finite sequence of edges such that the end vertex of one edge in the sequence is the start vertex of the next, and in which no vertex appears more than once. For part B, we have to state with a reason whether the network in figure 2 is Eulerian, semi-Eulerian or neither. Well, let's find out the order of the vertices. We've got 3 for A, 4 for B, 3 for E, 3 for C, 6 for F, 3 for H, 3 for G, and 3 for D. And what you can see here is we've got 1, 2, 3, 4, 5, 6. So it's neither Eulerian or semi-Eulerian because it's got 6 odd vertices. And that's what we see here. Figure 2 represents a network of cycle tracks between 8 villages A, B, C, D, E, F, G and H. The number on each arc represents the length in kilometers of the corresponding track. Samira lives in village A and wishes to visit her friend Daisy who lives in village H. We have to use Dijkstra's algorithm to find the shortest path that Samira can take for part C. So for part C, we've got this diagram here, and we've got this key. We've got the vertex, the order of labeling, the final value, and our working values. Now we are starting off at A, which means the order of labeling is 1, and we start off with the 0. Now, if I do 0 plus 4, I get 4. 0 plus 12 is 12. And then I've got the 0 plus the 10, which is 10. The smallest one from all of these is this 4, which means that we put the 4 into the final value, and we've got order of labeling 2 for B. Now, working from B, 4 plus 13 is 17. 4 plus 7 is 11. 4 plus 15 is 19. So now if I compare the 17, the 11, the 19 and the 10, you can see 10 is the smallest one. So 10 goes here. D has order of labeling 3. 10 plus 8 is 18. 10 plus 11 is 21. And so the smallest one from 21, 18, 11 and 17 is 11. So 11 goes here. 4 would be the order of labeling for C. Now, if I do 11 plus 3, that will be 14. So now, the smallest from 14, 21 and 17 is the 14. So the 14 goes here. F has order of labeling 5. Now if I do 14 plus 6, I get 20. 14 plus 20 is 24. 14 plus 4 is 18. I don't need to consider that. So the smallest one from 17, 24 and 20 is the 17. So 17 would go here. E has order of labeling 6. 17 plus 5 is 22. And the smaller one from the 22 and the 20 is the 20. So 20 would go here. G has order of labeling 7, and if I do 7 plus 12, or the 20 plus 12, I get 32, which is bigger than the 22. So naturally the 22 would go here, and then 8 would go here. So we have completed this algorithm, and now if we find the shortest path, well, the shortest path, we have to go from A to B, then we have to go from B to E, and then we go from E to H, as we see here. So that path is given by A, B, E, H. Next, an extra cycle track of length 9 kilometers is to be added to the network. It will either go directly between C and D or directly between E and G. Daisy plans to cycle along every track in the new network, starting and finishing at H. Given that the addition of either track CD or track EG will not affect the final values obtained in C, we have to use a suitable algorithm to find out which of the two possible extra tracks will give Daisy the shortest route. Making a method and working clear, you must state which tracks Daisy will repeat in her route, and we have to state the total length of her route. Now let's consider the situation with CD included. So what we are saying here is we've got CD, which is included, and it's got a length of 9. Now if I find out the odd vertices, well, here I've got 3, I've got 4, then 3. Now C has got 1, 2, 3, 4. D has got 1, 2, 3, 4. G has got 3. H has got 3. And F has got 6. And so, what you can see is the odd ones are A, E, G, and H. So, for the odd vertices, we've got A, E, G, and H. So what we now need to do is find out the possible pairings. So we could have A and E paired with G and H. And if I work out what this is, A to E, well, what we found before is that's 17. And we are going from G to H, so that will be 12. We could also have A to G added to EH. So if I work out what this is, I've got AG, so AG we found that to be 20. And E to H, that's 5. And we could also have AH added to EG. I'm working this out. A to H we found to be 22. And E to G, well, the quickest route is to go from E to F to G, so that's 4 plus 6, which is 10. So if I work out these totals, I get 29. Here I would get 25. And here I would get 32. So those are my pairings with CD included. Now with EG included, as we see here, as before, what we need to do is find the odd vertices. For the odd vertices, well, first of all, we see that A has got 3, B has got 4, C has got 3, D has got 3, F has got 1, 2, 3, 4, 5, 6, E has got 4, H has got 3, G has got 3. So the odd vertices here will be A, C, D, and H. So we've got A, C, D, and H. And now what we can do is find out the pairings. So with the pairings, we could have AC to DH. We could have AD and CH. Or we could have AH and CD. So A to C, that's just 11 because we've got the 4 plus the 7. And D to H, that will be given by 8 plus 4 plus 5, which is 17. So that's the shortest way. A to D, well, that's just 10. And then C to H, we're going from here to here. So the quickest way of getting there is 3 plus 4 plus 5, which is 12. And then A to H, we know that's 22. And then C to D, that will be 3 plus the 8, which is 11. So working out the totals, in this case, we've got 28, 22, and 33. So the smallest number we see here is this 22. So, because 22 is the smallest, well, we've got AD, which is being repeated, and then we've got CD. Now the way we can go, rather we've got CH. The way we can go from C to H, we said that was CF, then FE, and then EH, So what we can see here then is we would repeat AD, and then we've got CF, then we've got FE, and then we've got EH, which are repeated. And for that to happen, what we need to do is include EG, because with that condition we ended up with this 22. So what we have to do now is track EG in this case. So now for the total length, well, what we've got is the 120. So we've got the 120, and then what we do is we add on the 9, and then we add on the 22. So the total length is equal to 151 kilometers. So that's the total length. Question number 4. Figure 3 shows the constraints of a maximization linear programming problem in x and y, where x is greater or equal to 0 and y is greater or equal to 0. The unshaded area, including its boundaries, forms the feasible region R. An objective line has been drawn and labelled on the graph. For part A, we have to list the constraints as simplified inequalities with integer coefficients. Now, the way to approach this question is to work out the equation of each of these lines. So, this line here, well, it passes through 0, 14 and 14, 0. So this line would have equation x plus y equals 14. We can rearrange this inequality so we've got y equals. If I rearrange for y equals, we would have y equals 14 minus x. And the reason I want to write it as y equals is because then it's quite easy to have the correct direction of the inequality. Now, if I find out the equation of this line now, well, it passes through 6, that's fine. And then the gradient of this line, well, if I go 2 across and then 1 up, that means my gradient is a half. So here I've got y equals 1/2 x plus 6. That line there. And for this line here, well, to find out what this line is, first of all I need to find the gradient. Well, you can see I go 1 across and 3 up, so my gradient's 3. And then it passes through this point, which has coordinates 7 across, 6 up. So this line is y minus 6 equals the gradient, which is 3, times by x minus 7. And if I rewrite this equation, we would have y equals 3x minus 15. So I've got the equations of the lines, and therefore, if I find out the inequalities, well, here I've got y, and then I've got 14 minus x. Now I want the region below, that's where my feasible region is. So I want y to be less than or equal to 14 minus x. Then if I consider the 3x minus 15, so I've got y, and then I've got the 3x minus 15. I want everything above this line, so I want y to be greater or equal than 3x minus 15. And if I consider this line here, where I've got the y and the 1/2 x minus 15, rather the 1/2 x plus the 6, I want everything below this line, which means y is less than or equal to 1/2 plus 6. So I have 2y being less than or equal to x plus 6. And then I've also got the constraint x and y are both greater or equal than 0. So these are my inequalities, which satisfies this feasible region. For part B, the optimal value of the objective function is 216. We have to calculate the exact coordinates of the optimal vertex. So what we can do here is use the ruler test to find out where the coordinate first lies. So if I've moved my ruler up like so, you can see my optimal vertex is over here. So this point here is my optimal vertex. And to find that optimal vertex, what I need to do is solve this line simultaneously with this line. So what I can do is set 1/2 x plus 6 equal to 14 minus x. So for part B, for the first part, I set the 1/2 x plus 6 equal to the 14 minus x. So now let's solve for x. If I multiply through by 2, I've got x plus 12 equals 28 minus 2x. So we have 3x, which is equal to 28 minus 12, which is, well, if I take away 2, I get 26. So I get 3x is 16, which means x is equal to 16 over 3. And now I can find out what y is. So therefore, y is equal to 14 subtract 16 over 3. So if I work this out, I get 26 over 3. So I have 26 over 3. So therefore, the optimal vertex that has coordinates 16/3 and 26/3, which is that point over here. So now what we need to do is derive the objective function. Now it passes through 0, 4 and 10, 0. So that means for the next part, the objective function is of the form p equals some constant k multiplied by 10y plus 4x. And the reason we multiply by some constant k is because that will allow us to have the correct objective function. So we know the optimal value is 216. So I've got k times by 10y plus 4x equals 216. I know what y is and I know what x is. So I've got k multiplied by 10 times by 16/3 plus, rather, 10 times by 26/3 plus 4 multiplied by 16/3, and this is equal to 216. So I've got 10 times by 26/3 plus 4 times by 16/3, and if I do 216 divided by this, I get 2. So I get k equals 2. And knowing that k is 2, I can replace 2 over here. So my objective function, I've got p equals, well, I've got 4 times by 2, which is 8. Then I've got the x, and then I've got 2 times by the 10, which is 20, and then I've got the y. Here is my objective function. Given that x represents the number of small flower pots and y represents the number of large flower pots supplied to a customer, we have to deduce the optimal solution to the problem. First of all, this optimal vertex, if we were to write this as a mixed number, we've got 5 1/3 and 8 2/3. And what we can conclude from that then is that we require 6 small flower pots and 8 large flower pots.